The visible lines in the spectrum of hydrogen are known as the Balmer series of lines. These are lines due to transitions from quantum states with n larger than 2 to n equals 2. So if your energy levels look like this, n equals 1, n equals 2, n equals 3. One thing you'll notice, these energy levels are going to be, a lot of energy levels are going to get closer and closer together as you approach n equals infinity, okay, or e equals 0. So transitions from 3 to 2, 4 to 2, 5 to 2, and so on, that's known as a Balmer series. That's what's responsible for the lines that you see in the visible spectrum of hydrogen. Okay? And one thing you'll notice too is that since these energy gaps are getting smaller and smaller, the gaps between adjacent lines will eventually, as you get to shorter wavelengths, that means as you get to larger delta E's, it will converge. Okay? The gaps get smaller and smaller, and you can a nice website where you can get this, see the spectra for various atoms would be one at the University of Oregon. So you just Google Oregon atomic spectra. And that's going to be the first hit you'll find on Google. So this is a really nice website. If you click on emission here, you can see this is the visible spectrum of hydrogen. That's lithium, that's sodium, okay, and that's carbon. So let's take a look at hydrogen. And if you remember this right here, you click over this line right here, you can see that's 656, it's around 656 nanometers. Okay, so this is the 3 to 2 transition. So from n equals 3 to n equals 2, that's the first line in your Balmer series. This one is the second line in your Balmer series, n equals 4 to n equals 2. And this is from n equals 5 to n equals 2. So you're getting into shorter wavelengths. So right here, you're getting to shorter wavelengths. That means larger frequency, larger E photon, larger delta E going to the left. But notice the line spacing gets smaller and smaller. They will eventually converge somewhere here near just below the visible range. That will be, you will have here the transition from n equals infinity to n equals 2. Okay, so let's see. In fact, we can calculate this, at what wavelength the spectral lines would converge. That's going to be from n equals infinity to n equals 2. So delta E would be E infinity minus E2. E infinity is 0. Okay, that's negative 13.6 over infinity squared minus negative 13.6 over 2 squared. And that gives you 3.4 electron volts. So that's just negative E2 basically. Okay? And so from that you can calculate the wavelength. Now the ultraviolet lines in the spectrum of hydrogen, those are known as the Lyman series. Okay? From transitions to n equals 1. So if you look at this diagram right here, if you're going from something like the 2p orbital from n equals 2 to the 1s, that would be the first line in your Lyman series. That's going to happen in the ultraviolet region. That's called your Lyman alpha line. And then you can do n equals 2, and 2 to 1, 3 to 1, and so on. That particular series is known as the Lyman series. And what will be the convergence of that sequence of lines? That would occur at E infinity minus E1, which corresponds to a photon energy of 13.6 electron volts. In fact, that's the same value we get for the ionization energy, because that's the energy you need to bring your electron from the 1s orbital to n equals infinity, which is the threshold for removing the electron from the atom. Okay? So you just convert that photon energy of 13.6 electron volts, is E infinity minus E1. Just convert that to wavelength, and that will tell you what wavelength of light you need to knock off an electron from the 1s orbital of hydrogen.